This video is dedicated to proving the fundamental theorem of calculus. The fundamental theorem of calculus is one of the greatest human inventions. So far, we've been developing the idea of the definite integral. We've previously seen the derivative. This video will prove the connection between these two mathematical methods and show that they are inverses of each other. Two thoughts before I move on to the proof. Number one, throughout this proof, you might get a bit confused by some of the moves. You might be thinking in your head, oh my God, is this going to be on a quiz or an exam? The answer is absolutely not. The only part that you're responsible for is the actual theorem in the end. Though this is a really fun and interesting and important proof, it invokes a lot of stuff that you saw in differential calculus. And what it's going to do is to tie together these two main players, integration and differentiation, and prove that they're the inverse operations of each other. Second thing, I want to read you a paragraph that comes from the textbook where I first started teaching calculus. This is Stewart's Calculus. This is an old textbook. It's pretty beautiful. You can see it's being held together here strongly by some Gorilla Tape. But I want to read this paragraph so you really get the context for how big of a deal this is. The fundamental theorem of calculus is unquestionably the most important theorem in calculus, and indeed it ranks as one of the great accomplishments of the human mind. Before it was discovered, from the time of Exodus and Archimedes to the time of Galileo and Fermat, problems of finding areas, volumes, and lengths of curves were so difficult that only a genius could meet the challenge. But now, armed with a systematic method that Newton and Leibniz fashioned out of the fundamental theorem, we will see in the chapters to come that these challenging problems are accessible to all of us. First of all, we're defining g of x to be the definite integral from a to x of the function f. Importantly, in this case, where f has to be continuous on an interval a, b, and the x in this case has to come from the interval for which f is continuous. You don't want to get too deep in the weeds on thinking about this g of x function, but just to give you a quick visual of what's going on here, we have a function f that's continuous on an interval a, b. What we're looking to do is to define this function, and how we're defining it is by saying you're going to choose some x value between a and b, and this g of x function is going to output the area between the x that you choose between a and b and a. So it inputs this value x and it outputs this area between a and x. What we're looking to prove in this, the first part of the fundamental theorem of calculus, is that this g of x function is the mathematical definition of the antiderivative of f. Or in other words, the derivative of this g of x function is f. All right, the setup for the first part of the proof is we're going to consider this interval around x that's h units big, or from x to x plus h. Then what we're going to do is we're going to calculate g of x plus h minus g of x. Given our definition here above, these are the definitions of g of x plus h and g of x. What I'm going to do is I'm going to split up this integral into two integrals. I'm going to split it up from a to x and then add that to the integral from x to x plus h. And so all I've done here again is use that property we have for integrals, where if we go from a to x, then a to x plus h, that's the same thing as this integral statement right here. And why I'm doing that, you might be able to see this now, is that this is the same as this, except for this is being subtracted, this is being added. So these integrals cancel each other out, which tells me that g of x plus h minus g of x is simply this integral right here. So given this setup on this subintegral of x to x plus h, we have this statement right here. The next thing that we're going to do then is we're going to divide both sides of this equation by h. It's important to note that in this case, we're not going to let h be 0 at all. It can't be 0 because we can't divide by 0. This here is the first of our big steps in this proof, was proving this. So we're going to call this equation number 1. Then we employ our friend, the extreme value theorem. If you remember from differential calculus, the extreme value theorem says if you have a continuous function on a closed interval, then for sure that function reaches an absolute minimum and an absolute maximum. Or in other words, there exist values on this interval x to x plus h, so that the outputs of those functions are the absolute minimum and absolute maximum, meaning every other function value on that interval lies in between those two. Using that fact that the function values are bounded in between this maximum and minimum, then we know that if we evaluate this function on the interval from x to x plus h, that must end up being greater than this value of f of u times the length of the interval. And again, the length of this interval is h. So it must be greater than f of u times h. And it must be then also less than this constant value of f of v times the length of the interval h. Just to clarify this, from when you're looking back at the integral properties, this h was the b minus a, right? We took b minus a to find the length of that interval. For this interval that we're considering, we've already defined it to have a length of h. So then what I'm going to do is divide everything by h. Importantly, I didn't state it earlier, but I'm only considering the situation here where h is positive. You can prove this for h being negative. It's almost exactly the same. But in my consideration of this proof, I'm only going to make h positive because there's no issues then me dividing by a negative right here. So what I'm going to do is divide everything by h. So that gets divided by h. I'll just throw the division of h there and divide by h there. Obviously, what happens then are these h's get canceled. And what I get then is that f of u is less than or equal to 1 over h times this integral. Then, if I apply the equation number 1, I have the fact that this expression, g of x plus h minus g of x over h, is equal to this. This expression is the middle of this inequality, so I'm going to substitute this with this expression right here to get that f of u is less than or equal to g of x plus h minus g of x all over h is less than or equal to f of v. This right here was a sneaky big deal. What I started with was this integral that was equal to a function, but through these steps to right here, I now have a relationship between the function f and the function g. And as you might be thinking, man, this looks a heck of a lot like the limit definition of a derivative, and it is, and we're almost there. But importantly, before I move forward, this is going to be our equation number 2 that we're going to need to finish this proof off. All right, and so then what we're going to do, as you might guess, is we're going to consider what happens when h goes to 0. Importantly, remember, we're doing all of this work on the idea that we have this subinterval of x to x plus h. It has a length of h. Also, we found these x values here, u and v, that end up being that output this absolute minimum and absolute maximum, giving these boundings right here. Now think about this. If h goes to 0, so as h tends to 0, the size of this interval also goes to 0. And importantly then, if you consider when h is almost 0, this becomes an interval of almost no length. Meaning, as h goes to 0, the only representative point in here becomes x. So specifically, u and v go to x. Or in other words, mathematically speaking, the limit as h goes to 0 of f of u equals the limit as u goes to x of f of u, which is f of x. In exactly the same way, the limit as h goes to 0 of f of v becomes the limit as v goes to x of f of v, which is f of x. With those two limit statements and that logic, along with that second equation, and our old friend, the squeeze theorem, which you might remember way back from the beginning when you introduced the idea of limits, since the limits of these bounding functions on this expression go to the same thing, they go to f of x, it means the limit as h goes to 0 of this expression also goes to f of x. And that, my friends, is what we were trying to prove. We were trying to prove that given this setup, the derivative of this function equals f of x. And in this case right here, we have the limit of g of x plus h minus g of x over h, which is the derivative of g of x, equals f of x. All right, so that's the first part of the fundamental theorem of calculus. By the way, what we've just defined there is something you've probably seen before but never saw it in this notation. This is the definition of the indefinite integral. What I'm going to do now is I'm going to give you the second part of the fundamental theorem of calculus, which is also called the net change theorem, so that we have this holistic picture of what this theorem is, and then I'm going to go through and prove the second part. The second part of the fundamental theorem of calculus says that if we are trying to integrate from a to b of this function f of x, we're trying to evaluate this definite integral, we can do that by calculating big F of b minus big F of a, where big F of x is the antiderivative of f of x. All right, so again, the setup for this proof is this big F here is the antiderivative of the function f of x, or in other words, the derivative of the big F of x is equal to f of x. For this proof, what I'm first going to start working with is this side. So f of b minus f of a. If you remember to our idea of Riemann sums, right? B and a are just the beginning and end of all these little subintervals. So specifically, b is the same thing as xn. And a is the same thing as x naught, or that first partition point. Now I'm going to use this brilliantly simple technique in many proofs where I'm going to add a bunch of zeros to this expression. I'm creating a summation, right? And that should make sense. I should be trying to create a summation with this if I'm going to get this thing to turn into this. And so what I do is I'm going to add a ton of terms here, but I'm going to add terms that are equal to 0. So what I'm first going to do is subtract f of xn minus 1 and then add f of xn minus 1. And I'm going to do that with every interval value. I'm going to subtract f of xn minus 2 plus f of xn minus 2 all the way down, adding and subtracting those until I get to f of x1 and then minus f of x0. And again, just to clarify and visually make sure this makes sense, what we started with was f of xn minus f of x naught, and simply in between, we've added in a bunch of these zeros to make this summation. Now when we look at this, we can group these terms in this way. So I'll take these two, the next two, all the way down to these right here, where each of the terms now that I'm putting in parentheses is f of xi minus f of xi minus 1. Or in other words, this entire summation, which is equal to this, is the same thing as the sum from I equals 1 to n of big F of xi minus big F of xi minus 1. Now, the last of our friends that we need to help us out in this part is the mean value theorem. The mean value theorem, remember, if we have a continuous function on an interval, then we know that in that interval, there's a point that has the slope that's the same as the endpoints. Or in other words, this statement right here. For all of these little intervals that we've created, the ith interval, there exists some constant on that interval so that the derivative of that value right there is the same as the slope of these endpoints. So the mean value theorem proves the existence of that value that makes that happen. What I'm going to do now is multiply both sides by this denominator. And that is the beautiful sneakiness of this proof. By applying the mean value theorem and getting the existence of these c values, what we've shown is that this expression right here is how our summation right here that's equal to our original statement. These terms are defined by that. We can replace this statement with this. That doesn't seem that beautiful until you realize this. First of all, big F prime of Ci is equal to little f of Ci, because the big F is the antiderivative, or the derivative of big F is just f of x. And so this statement right here actually becomes f of Ci. And the x xi minus 1, well, that's the definition for this delta x, or the size of these intervals. And so we'll replace that with this statement. Then what I can do is rewrite this statement with these describing the terms. So let me write this all out real fast. We have f of b minus big F of a now equals the summation from I equals 1 to n of f of ci. Now little f, right? Now we have little f in here, or original function instead of the antiderivative. And then delta x. Then finally, we apply the limit to both sides of this equation as n goes to infinity. Importantly, these two expressions right here are constants. And again, constants aren't affected by the limits. So you apply the limit to this side, nothing happens. If you apply the limit to this side as n goes to infinity, well, you get the derivative of f, because this is any value being in these ith intervals being plugged into f. Again, that's we had that xi star that we talked about with the Riemann sums, giving us the fact that f of b, big F of b minus big F of a equals the integral from a to b of f of x dx. This video is very different than many of the videos I make. Usually in my videos, I'll show a new concept, maybe give a slight proof or a visual proof, often not a rigorous proof. I'll focus most of my energy on applying the concepts. This video is different, and because of what it is, this is massive. Most of the work that you've done through differential calculus was actually aimed at getting you to be able to understand this proof. We introduced the extreme value theorem. We introduced the squeeze theorem. We introduced the mean value theorem in differential calculus. And we saw maybe a little bit to prove the things that we're doing. But the big use of them is to prove these facts. And what this all says in part 1 and part 2, what we're saying is that the method of differentiation and the method of integration are very different processes, but they happen to be the inverse of each other, the exact opposites. If you apply differentiation to an integral, to a definite integral, they cancel each other out, or vice versa. This will have a major impact on everything that we have moving forward. And I hope that you do spend a little bit of time, if you're confused by parts of this proof, by looking at it, looking into the textbooks and seeing how they've shown the proofs. We're all probably pretty similar to these. This is the most modern method of proving the fundamental theorem of calculus. But I hope nonetheless, you can at least sit back and appreciate what this is and the power of all those theorems coming together in this one great proof.